completed this Indianapolis race car. It went on to win a lot of national races, the pole position at Indianapolis, and 2 national championships. This is the Indy 500 in 1934. 10 of the cars in this race were built by Stevens. The winning car averaged 106 miles an hour and averaged an amazing 14 miles per gallon of gasoline. The reasons? Lightweight, efficient engines, a low-slung front-wheel drive chassis, and a highly advanced, streamlined aerodynamic design. These racing cars were opening up America's automotive future 40 years early. A car passes the old wooden stands in Turn 2 and brings us back to the new aluminum stands around Turn 2. 400,000 people crowd in here on race day, but it's now November 1981, and the stands are empty. The huge Hall of Fame here at the motor racing capital of the world is open to visitors all year. This story of Myron Stevens' race cars and how he built them starts here at the Hall of Fame, where some of his greatest works are on prominent display. In the center stage, both sitting nose up to this massive trophy, are 2 famous Stevens-built cars. This is a 1925 Miller. A nearly identical Miller clocked a speed of 171 miles per hour with only a 91 cubic inch engine. It was advanced engineering, lightweight metals, and streamlining that brought such performance. An example of its painstaking construction is the small gear lever knob. It's not solid. To save just a few ounces, it's made of a hand-formed, thin-walled aluminum casting. The Miller race cars are today world famous as masterpieces of craftsmanship in metal. They are often called pieces of automotive jewelry. Myron Stevens made these exhaust headers, not from tubing, but from one flat sheet of 20-gauge steel. The first set took him 80 hours. Later, they took him only 40 hours. This car won the 1928 Indy 500, driven by Louis Meyer, Indy's first 3-time winner. He won all 3 in cars built by Stevens. The detail work is beautiful. Built by Myron Stevens, the streamlined body on this 1939 Indy car covered a very complex machine. It had 16 cylinders, 2 superchargers, 2 crankshafts, and put out over 500 horsepower from only 183 cubic inches. This one-piece, single-thickness tail on a 1925 Miller also holds the fuel. This is the first Miller front-drive race car. It was built by Myron Stevens. Its front-drive design eliminates the drive shaft under the seating area, allowing the driver to sit lower and for the car to have a smaller overall size and better aerodynamics. The car's height and size are apparent here. This is the patented front-drive unit on the 1925 Miller. This low-slung, aerodynamic front-drive chassis design used by the Miller race cars in the 1920s was a leading force in automotive development for 25 years at Indianapolis. Now in 1981, aerodynamic front-drive cars dominate the world passenger car market. And these lightweight, meticulously built pieces of artwork and metal had to perform too. Not just hang on a wall or sit in front of a building. They raced 500 miles on a rough brick track at Indianapolis. The camera in one 1930s race car shows just how rough it was. Some drivers could even get them to fly, but not far. These are the hands and hammers of Myron Stevens. In November of 1981, Stevens, then 80 years old, left his comfortable retirement home in Arizona, and with the same tools he had used 60 years before to build the world's most perfect cars, demonstrated how it was done then. and can be done now. With sheet aluminum being used in many passenger cars in the 1980s, in hoods, deck lids, interior panels, and with sheet aluminum useful for aerodynamic spoilers, performance, and custom work, Stevens' skills should be passed on and continued by those who will. And with the widespread use of aluminum in modern cars, it becomes important that Stevens' craft needs only common shop tools, tools that are available today in nearly every small automotive shop. The aluminum used in this demonstration, where Myron will form an aluminum body piece, is currently available. It is sold as grade 3003-0 and is 63 thousandths of an inch thick, the same as Stevens used in his race cars. It's common today to anneal or soften aluminum in special furnaces. Myron will use only a torch and pieces of wood. It's also common to make difficult curves in aluminum by using specialized machinery. Myron will use only a hammer and dolly. And for welding sheet aluminum, Heliarc and other expensive welders are used today. Myron will use just this common acetylene torch outfit. The acetylene pressure is set at a normal reading, 5 pounds. The oxygen pressure is set at 10 pounds. For welding, Myron will use a small O tip and a large tip for heating. These are the tools used in this demonstration. The individual tools and equipment will be described in more detail after Myron has used them to form the demonstration piece. He begins. He is using the torch with the number 4 tip to heat the sheet until it is annealed or softened for easy shaping. A thin layer of sawdust has been spread over the sheet. When the sawdust begins to burn, turning dark brown across the sheet, the aluminum is annealed. The heat must then be turned off, or the metal will melt and drop away very suddenly. The annealed sheet has been bent around a pre-built angle iron frame that has the exact radius curve Stevens wants. He and Mike, a young worker interested in learning the trade, clamped the aluminum to the frame. The piece Myron is making will have compound curves and is similar to the rounded top of a race car's nose. The aluminum must be cut before bending and shaping, and measurements are made for 2 parallel cuts. The cuts are positioned exactly in the middle of the radius of the 2 curves. Metal shears are used to make the cuts. Stevens bends the first side around the angle iron frame. He was 17 when he went to work, starting as a body man's helper at a Los Angeles auto body shop, learning the trade by repairing cars and helping build custom bodies. He says, "I'm glad that as a kid I had the sense to go to work doing something I liked." Here both men bend the second side and then clamp it to the frame. During bending and clamping, some metal has to be cut from the 2 ends of the curved side pieces so they meet exactly for welding. The two ends have now been trimmed so they meet and are hammered for a final close fit just before welding. Mike, using white welding flux made into a paste, coats the rod. Using the small O tip, the flame is set for welding the 1/16 inch aluminum. The flame's inner cone is less than 1/2 inch long. Modern welding manuals explain the process in more detail. The first tack is applied and must be allowed to cool before another is done to prevent cracking of the first tack. Since heating twists the aluminum and pulls the sides apart, they're brought back together before the next tack weld. A beginner in welding sheet aluminum should start with a short, cool flame for better control of the heat. The tack weld should be spaced about 3/4 of an inch apart. Mike is first spot tacking this seam together because the metal would have flexed, moved apart, and the weld would have cracked if a continuous seam had been applied at the beginning. Watch the position of the rod. It is kept just out of the flame until the exact moment of welding to prevent the rod end from overheating and dropping off. The welds are hammered to flatten them before the seam is welded. A couple of them cracked, and they were repaired before the continuous seam was welded. Mike begins welding the continuous seam, welding right over and through the tacks. Watch the motion and angle of the tip and rod as he moves. Then, just before he stops, he uses too much heat, and a small hole opens suddenly. It was filled with weld before he continued. Mike has experience welding other metals, but has been welding aluminum only 4 days under Myron's direction. Myron's welds years ago were flatter and more even due to his experience. But in 1981, eye cataracts and lens implants prevent Myron from welding. Myron rated Mike an excellent student. Too much heat at the top edge and another hole. Luckily, this area was eventually to be trimmed off. After the metal cools, Myron uses a felt tip marker to indicate where a piece should be removed from the top flap of the nose piece. Later, as the edge of this top piece is being hammered down to meet the lower edges, we'll see how accurately Myron estimated the cut. The piece is being cut off now to give clearance for hammering down and shrinking the side pieces that were just bent and welded together. Stevens begins the process of shrinking down the side pieces to form the nose piece. He uses heat to soften the area he's going to shape. It's been about 30 years since Myron has worked a piece of aluminum. In the 1920s and 30s, he built as many as 10 to 12 cars each year. And there were so many cars. A recent magazine story reveals that Stevens built a famous two-time Indy pole position winner, not another man who had been given credit for it. Myron had completely forgotten building the car. By hammering away from the dolly, not directly on top of it, Stevens is able to move the metal down and its outer edges in toward the center to form the curve. The dolly is positioned farther down in the picture than where the hammer is striking the metal. He uses heat again to warm the aluminum and the matchstick to check its temperature. And watch how quickly this bump is flattened. As he heats this area to soften it for easy shaping, he checks the metal's temperature with the wooden end of a kitchen match. When the wood touches the hot metal, it will leave a noticeable brown streak as soon as the metal is hot enough to work. Look at this picture carefully. The dents in the metal show evidence of where the dolly is being held. Again, the hammer strikes nearer to the metal's edge than the dolly is being held. During this process of shrinking the metal, the distance across the top edge of the area being hammered here will decrease, meaning that the metal is actually becoming thicker. The hammer strikes the metal away from the dolly, meaning not on top of it, because hitting directly on top of the dolly would flatten and therefore stretch the metal, a useful skill in doing other curves. The last major step in forming our nosepiece is to shrink down the top flap to meet the sides. Again, the torch is used to soften the metal. Here Myron uses the edge of the hammer and the edge of the dolly to move the metal more quickly. Watch carefully the relative positions of the edge of the hammer and the edge of the dolly as they meet to form the metal. Although it looks the other way, the edge of the hammer is again hitting the metal closer to the edge of this top flap than the spot where the edge of the dolly is held. So far, about 2 minutes of actual shop time have passed since the first heat was applied to this top flap. Watch the positioning of the dolly here. Its edge is further toward the bottom of the picture than the hammer. This is the fourth time heat has been applied to this top flap for working. The technique used to shrink the metal here is probably best learned by watching carefully. And of course, some days, even artists like Myron Stevens have their problems. Here the dolly is being held under the low spots in the metal, while the hammer hits the high spots. The dolly is again further away from the metal's edge than where the hammer is striking. When most people glanced at Myron Stevens, they thought they saw a body man or a mechanic. But the cars he quietly built opened doors to the future, a future of small, lightweight, fuel-efficient, front-drive aerodynamic cars. And maybe he was more. Many call his work fine sculpture in metal, art that functioned, art from an auto shop. He hand-built this chrome-plated grille simply by positioning and spot welding pieces of small welding rod to form the crossbars and larger diameter for the vertical bars. It takes experience to learn a craft such as this one and to do it well. But some people learn very quickly. Stevens began as a bodyman's helper in 1918, and only 4 years later, built beautiful Miller cars that finished first, second, third, and fourth in the Indianapolis 500. This is the sixth application of heat to the top piece. Since the first heat was applied to this top flap, only about 20 minutes of actual shop time has passed. In 1981, there were probably less than 30 people in America who can hand form aluminum with common shop tools. Myron hasn't gained fame from his Indy cars, and he probably explains that best by saying, "I didn't spend much time talking to riders or racing officials. I had work to do." The 1981 camera crew saw his work habits. He didn't even want to stop for lunch during the all-day taping session. The piece is now ready for spot welding and trimming. Here Mike uses a chisel to cut excess material from the top flap. One short weld has been put in the center to hold the edges together. Following chiseling, the edges were hammered, again trimmed to match. More tack welds were put on, and the whole seam was welded. After the seam has been welded and partly finished, Myron heats a high spot before shaping it. He uses the rawhide mallet on rougher areas such as this one, and then the steel hammers for final finishing. Watch how quickly this area is smoothed down. Myron explains the sideways motion of the steel hammer in finishing the metal by saying that if he hit straight up and down, the hammerhead would block his vision of the area he's striking. But by moving the head sideways after each blow, he can see the effect each single impact of the hammer has had on the metal. The sideways motion also provides a slight smoothing action for finishing. He has an amazing record. Cars that Myron Stevens built won the pole position at Indianapolis 11 times, won the race 8 times, finished second 16 times, and third 7 times. And the Stevens legacy continues at Indianapolis. Men he taught the craft built 7 more 500 winners, and these men taught others that built significant American racing cars through the 1960s and today. The entire process, since the flat sheet was annealed with the sawdust on it, has taken less than 4 hours of shop time. Even the weld areas on the inside of a body piece were hammered flat and smooth in a Stevens car. The final contours of the machines weren't determined by any form or mold. They were done simply by the hands and eyes of this artist in metal. A flat Vixen file is used in the final process of smoothing our nosepiece. This is a process that very quickly smooths out the little bumps in the metal. Here the Vixen file is used on the weld, smoothing it out. Sanding the metal and chroming or painting it are all that remain to be done. Here are the individual tools. The welding rod can be bought at most welding supply houses. Ask for 1/8 inch pure aluminum welding rod. Cobalt blue lenses, also bought at a welding supply store, make it possible to see the aluminum turn a reddish color just at the instant it should be welded. Also bought at the welding supply store was this powdered aluminum flux. The flux was mixed with water to form a paste, which was brushed on the welding rod before it was used. In welding, an O tip was used for a cool flame. For heating a large sheet to anneal it, making it soft and workable, this rosebud tip would be fast. But Stevens was more familiar with this number 4 tip on the left. Common wooden kitchen matches were used for checking the temperature of the aluminum to see if it was annealed and ready to work. Myron designed these hammers and hand-forged them in 1921 using steel from Model T axles. They're lightweight and easy to use over long periods. Hammers like this are sold at many stores today. This rawhide mallet is also commonly available. Vice grips of assorted shapes and sizes were needed. About 12 pair were used in this demonstration. Good metal cutting shears were also needed in left cut, right cut, and straight cut versions. These chisels were used for trimming edges. This flat Vixen file was used at the end of our demonstration for final smoothing of the metal. This curved shape would be used for filing inside tight corners. An assortment of dollies was needed for holding inside the metal when shaping with a hammer. When the demonstration was over, Myron carefully put his tools away and said, "You know, I just wish I was young and physically able. I'd like to start in and do the same thing all over again." Funding for this program was provided by the International Association of Machinists and Aerospace Workers, who are carrying the pride of their nearly 1 million craftsman members and the Myron Stevens tradition of automotive quality into the world of Indy car racing in the 1980s.